like the newer tests, but then the keys don't line up.
Yeah, I don't know. I guess I got them all mixed up. And so, did you take a look? I posted another key this morning. Did it match? It still didn't match?
Wait, which one?
Oh. Well, I did two keys, the wrong keys then. Do you have questions about the test I posted then? We can go through and...
What does it mean by like the amount of d orbital hybridization in sp3d and sp3d2 is unresolved?
Okay, so what does it mean about the d orbital hybridization or participation of d orbitals? So so there are two camps here for expanded octets. One is you could use d orbitals. So let's call it d orbital hybridization. And so if we use the s and the p orbitals, we max out at 8 electrons, an octet. And so if we can incorporate some d orbitals into the hybridization, then we can expand it further beyond 8 electrons. We'll go up to 10 and 12 electrons. And if we do d orbital hybridization, then we come up with these new hybrid orbitals. So we max out here at 8, but if we included a d orbital in the hybrid, then that adds another 2 electrons. And if we do sp3d2, we'll get a total of 12 electrons altogether. And so this was the hypothesis. You could only do this if the n were the same. So we have to have ns, np, and nd, where n is the same. They're all equal n. So you wouldn't be able to do this in the second period because there's no 2 d orbitals, but you could do it for the third, the fourth, the fifth periods on up. And so this hypothesis has been around for a long time, and so people treated it as theory, basically. You know, the theory underlying these expanded octets is d. But what can happen with theory is there could be some new observations, and these new observations make you question the original hypothesis. This is the same thing that happened with Bohr. You know, he came up with a hypothesis, the Bohr orbits, but there's some problems with that. And it turns out there are potential problems with this. You know, we could have d orbital hybridization, or we could have pd pi bonding. If we have pd pi bonding, that would also allow one to expand the octet. And so let's say we ran out of p orbitals, we could utilize a d orbital in pi bonding. A new hypothesis came along, which seems to be supported by the quantum mechanical calculations. And so this new hypothesis came along saying that there's very little d orbital participation based on their calculations. When they do their quantum calculations, they can mix all the orbitals. And it turns out they don't have to mix d orbitals in with their calculation. Okay, let's see. Okay. So the new hypothesis is there's no d orbital participation. Max at 8 electrons, which is an octet. So we don't exceed an octet. And so this is why in class I call this the octet law rather than the octet rule. The law, you know, should have more rigor, I mean, as far as conformance and violations. But whereas a rule, yeah, so much, so we can violate. Octet rule, we will violate when we have less than one octet. That hasn't changed. But when we have more than one octet, then that's it. So what was the question?
The non-d orbital hybridization in sp3d and sp3d2 is unresolved.
Yes. It's unresolved because this new hypothesis, we should like more data for this. And so when we have more data and then we shift, because once it becomes resolved, then we can just get rid of this. Let's say there is no d orbital participation, then there's no reason to continue teaching sp3d and sp3d2 hybridization. There's no problem with sp, sp2, sp3. That hybridization is fine. It's just these ones with the expanded octet. And so the picture over here is that we have 4 bonds, and any extra bonds are going to be not covalent, but they're going to be what? Ionic. And so we have 4 covalent bonds max, and then anything extra. 4 covalent bonds, there could be a lone pair in there too, so it's not necessarily bonds. But any extras, like for example, the one I talked about was SF4. SF4 has a lone pair there that's going to take up an orbital. So we would call this sp3d hybridization. But the theoretical calculations, because the computers are getting better and better, and they can do more and more accurate calculations, the d orbital participation is questionable. Maybe there is no d orbital participation. If there's no d orbital participation, then we can't fit this many electrons on sulfur. So the d orbitals are empty. So where are the electrons going to go? Well, they don't go anywhere. Instead, we describe the bonding differently. The bonding in SF4 is going to be a mix of covalent and I could pick any of these fluorines to form the ionic bond. I just picked this one. I don't know why. This is the one I didn't class. So this is negative. Yeah. This is not a bond. So I should draw it further out. And so in this case, I have 3 bonds, the lone pair, that's going to occupy my 4 valence orbitals on sulfur. And this extra one doesn't go. So if this is fluoride, then it's taking the electrons from sulfur. And so sulfur ends up with 1, 2, 3, 4, 5. And so sulfur ends up with a positive charge here. And so we say it's an ionic bond here. And then we can draw 4 resonance forms. That is, we just move the ionic bond here, here, and here. Now the shape of this doesn't go tetrahedral. And we don't call this sp3 hybridization, even though it's got an octet. The angles are going to be still like this, the seesaw shape. That is, it's going to be trigonal pyramidal type electron geometry here. And so based on that study, the study supports this. And the study does not support this at all. But it hasn't been abandoned yet. Otherwise, the book wouldn't spend so much time. The Bohr model has been completely abandoned. So even though the book spends time talking about the Bohr model, nobody uses the Bohr model anymore. But people still use this. So for example, if you go onto Google and do a search for the structures, you'll see this. Well, that means sulfur has 2, 4, 6, 8, 10, 12, 12 electrons. We're going to put the extra 4 electrons. You know, once we fill the s in the p orbitals, then there's no more room left. It was sure convenient to throw those in the d and then hybridize everything. But we can't throw them into the d. If these calculations are correct, somebody's got to repeat these calculations. Sure. So what I said was this: to be on the safe side, we'll just not violate the octet rule. So what they're saying is that we don't have to form 2 PD pi bonds. What we have is we have a mix of covalent and ionic bonding. So this might look like a single bond here, but this is not a single bond. This bond consists of one covalent bond here, which would be an sp3 sigma bond. Do you see that here? And so we'd have one covalent bond, sp3 sigma bond, and then one ionic bond. The ionic bond is going to be the negatively charged oxygen being electrically attracted to the positive 2 charged sulfur. And so that would be your double bond. Whereas over here, there's no ionic component to this bond. It's primarily a covalent bond, polar covalent bonds here. This would be an sp3 sigma bond here. So the book goes into electron density maps and all that stuff, but I skipped all that, the electron density maps. Otherwise, it would take even longer to discuss this. We looked at all the evidence pointing to this. Okay, are there other questions from that test, since I didn't post the key? I don't know. I don't know. You have the other 2 keys, so maybe use those as additional practice.
You said the acid-base questions weren't going to be on this exam, right?
Right, the acid-base. On the test that I posted online, did it start off with an acid-base question? There were a lot of acid-base questions on the practice test I put online. Yeah, it depends on, each semester I get to a different point. The acid-base questions will be on the final exam. You aren't going to have any acid-base questions on this test. And some years I cover acid-base chemistry in more detail, other years I don't. Depends on how much time I have, how far behind I am. And so, yeah, that will be on the final exam. Acid-base questions and MO theory. And then there's another thing, estimating delta H of reaction. Estimating delta H of reaction is super simple, so I was thinking I'll put it on this one, but I decided not to. One thing, though, that I did skip, when I was making the key up, I realized I skipped this. And this is with ionization energies. The trend in ionization energy goes with size. So let's start off with lithium. Lithium's kind of big for the second shell element. And if we look at its ionization energy, it's fairly low compared to beryllium. Beryllium's smaller, so we expect its ionization energy to be higher, harder to ionize. We go to boron. Boron's even smaller, and so we expect it to be harder to ionize boron, but it turns out it's not harder to ionize boron. It turns out to be easier than expected to ionize boron. And so boron's an exception. Even though it's smaller and should be harder to ionize, it's easier to ionize. And so why is that? And so the reason why that is because when we look at beryllium, we're ionizing a 2s electron here. But for boron, we're not ionizing a 2s electron. We're going to ionize a 2p electron. And so ionizing the next subshell, from the 2s subshell to the 2p subshell, this next higher energy subshell will be easier. So it makes boron easier than expected, even though its size is smaller. But once we go to carbon, then we're back on the trend, because carbon, we're just ionizing a 2p, so it's a fair comparison. A 2p on boron versus a 2p on carbon. Well, 2p on carbon is going to be harder to ionize because carbon's smaller. So carbon resumes the trend, it's smaller. And then we go to nitrogen. Nitrogen's also ionizing a 2p, and it's smaller, so it should be harder to ionize. Sizes. And we expect carbon to go up, but carbon's unusually easy to ionize compared to nitrogen. Why is that? And so carbon is another not carbon, oxygen. Oxygen is another exception here. And so oxygen is smaller yet, but easier to ionize. Why is that? And so when we look at nitrogen, we're ionizing one of these 3 2p electrons. However, when we look at oxygen, let me do it in blue. When we look at oxygen, which of these 4 2p electrons will be easiest to ionize? The which one?
The spin down.
Yeah, the spin down. This one will be easier to ionize. There's a reason for that, and that's because of electron-electron repulsions. So electron-electron repulsions is going to give us a little boost compared to nitrogen that we see here. So even though oxygen is smaller, it's easier to ionize. So on the practice test, I had this. Which one's easier to ionize? It turns out like oxygen's easier to ionize. I can't remember how I had it. And so the ionization energy goes down. Maybe I wrote it like this. Oxygen has a lower ionization energy than nitrogen. We don't expect that. We expect oxygen to have a higher ionization energy than nitrogen. It should have a higher ionization energy because it's smaller. But once we pair, then fluorine's going to have 2 paired ones, so we'll just ionize one of those. Fluorine's even smaller. And then finally neon. Neon's going to be the hardest of all these to ionize. It's the smallest, so it gets smaller and smaller as we go across. So the 2 exceptions are oxygen and the boron here. This is the second shell. When we go to the third shell, the exact same thing happens. The third shell, we're going to see the same kink going from magnesium to aluminum. There's a kink there, and then going from phosphorus to sulfur, there's another kink here. And so we see a repetition of the kinks. However, when we go to the fourth shell, fifth shell, these kinks become less pronounced because the orbitals grow bigger. As the orbitals grow bigger, electron-electron repulsions are less significant. And so here in the 2p orbital is kind of small, so the repulsions are greater. In the 3p orbital, there's more space, and the repulsions aren't as great, so the blip isn't going to be as big. So this blip goes smaller and smaller as we go across. And so that's the blip in the ionization energies. So that was something I skipped over. Planning to come back to it, but I didn't. Okay, other questions from the test? I may make the key for it. Let's see how much time I have. The key, but I already made 2 keys, I think. Did anybody attend the Mesa session? I think I asked the other day. But I gave her one of the keys, or both of the keys, but I asked morning and afternoon, but nobody went, I think, so not sure.
For Mesa tutoring for Chem, it's during our class period.
Yeah, that's what I thought. And so the morning class, nobody went. Okay. I don't know why they schedule it that way. But if another question comes up, let me know. Otherwise, I want to continue talking about acid strength, base strength. Since I have this written up here, I might as well talk about this one here first. And that is a sulfuric acid versus sulfurous acid. Well, sulfurous acid, we have the same thing. We could expand the octet, get rid of formal charge. So we end up with around sulfur 1, 2, 3, 4, 5, 6. But, you know, we had to expand the octet by doing 1 PD pi bond here versus 2 PD pi bonds over here. Maybe this is okay, you know, 1 PD pi bond. Or we don't bother expanding the octet. But the problem here is that, okay, this is fine. We don't expand the octet. The octet's the max, and then we have this ionic contribution to the bond. That kind of makes the double bond there. But, you know, the theory has to have widespread acceptance. And so there's still people who are going to do the d orbital hybridization. And so, unfortunately, you need to know that. If it was widespread acceptance and you didn't have to do that, then I would skip it entirely. I mean, save a lot of time that way. However, since we're going to jump on and so you could just leave it as an octet and have this ionic contribution here, and same thing here. Problem with this is, like, if you go to Google, 99.9% of the structures look like this. If you do an image search. And so you need to be aware of what's going on with that and why they did it that way. But for us, go ahead and not expand the octet. Just we kind of get the same answer, something similar. Doesn't come off too terribly bad. But what can you tell me about why would sulfuric acid be a stronger acid than sulfurous acid? Well, different ways of explaining it. This one we could use formal charge if we wanted to. You know, if we think about the electronegativity of a +1 sulfur versus electronegativity of a +2 sulfur, which one's more electronegative? Yeah, this one, +2 sulfur. If the +2 sulfur is more electronegative, it's going to have a stronger inductive effect. That is, it's going to withdraw more of the electron cloud away from ultimately the hydrogens here. And therefore, these hydrogens are much more positive than these hydrogens over here. So this is a weak acid. This is a strong acid. When I compare these two structures, though, is there any formal charge? There's no formal charge. All the formal charges are 0. So how are we going to do this? Well, let me show you how they do this. In organic chemistry, they do it like this. You have one terminal oxygen here that's sucking electron density. And in turn, that's going to suck the electron density away from the hydrogens. So we have the inductive effect here. Over here, we have two terminal oxygens pulling electron cloud density from sulfur, which is going to result in a stronger inductive effect, which is going to result in more electron cloud density being removed from the hydrogens, making those hydrogens more polar than these hydrogens here. Does that make sense? Yeah. And so the more oxygens you have there, for me, I like to do it using oxidation state too. When we look at the oxidation state, what is the oxidation state on this sulfur? Well, these two belong entirely to sulfur because there are no other atoms. And so that's 2, and then oxygen takes all. So 0, oxygen takes all, that's 0, oxygen takes all, that's 0. So sulfur only ends up with these 2 electrons from the lone pair. All the other electrons are taken by oxygen. Oxygen, it's winner take all, and the winner is the more electronegative species. So if sulfur ends up with 2 electrons, how many is it supposed to have? 6. So what's the charge? Plus 4. When we go over to this sulfur, how many electrons does sulfur end up with? None. It's supposed to have 6. It ends up at plus 6. This is max. We aren't going to be able to take any more electrons away from sulfur. It's maxed out. And so the same thing goes here. A plus 6 sulfur versus a plus 4 sulfur. Plus 6 is going to be a lot less electron rich. It's going to be quite, in fact, the opposite. It's going to be quite electron poor. And that's going to have a stronger inductive effect. So inductive effect is important. What else do we look for? We look for the bond energy. The bond energy is going to be about the same. They're both hydrogen-oxygen bonds. And then we look at bond polarity. And then what else do we look at? We look for stability of the conjugate base. So let's do that next here. Let's compare the 2 bases. So an acid comes along and plucks off the H+, leaving behind the electrons. And what we'll do is this. This takes so much extra time.
I have an idea. Let's not learn it and also not be tested on it. Just considering it. You win, we win, it's a win-win.
It's not going to be a win-win when you get into some class and the person's only d orbital hybridization. Then you're going to be in trouble.
No, that would be a lose.
Yeah. And there's going to be people who are probably going to be, they need to be convinced more, than some simple calculation. It's not a simple calculation. All right, so if we lose the proton, then we end up with this structure. This is with the octet. This is with the expanded octet. This is where you're going to need it, because in organic chemistry, they're going to do it like this. And so if we look at it with the expanded octet, we end up with this. And automatically, you may be able to see this. What do you see about that structure there?
expanded form has a resonance form?
Yeah, the expanded should have a resonance form, and the resonance form is going to look like this. So in organic, they're going to be expecting you to write down all the resonance forms. But neither resonance form is accurate. What's the most accurate representation of this structure? The resonance hybrid. The resonance hybrid is going to be the most accurate representation of the structure. Anyway, the more resonance forms we can draw, the more stable it should be. But what will the hybrid look like? When we look at the hybrid structure, it's not a single, it's not a double. It's in between a single and a double. What's in between a single and a double? Like halfway between a single and a double would be a 1.5 bond. And so what we're going to end up with here is a 1.5 bond. How do you draw a 1.5 bond? You draw like the pi bonding electrons being spread out like that. And then this one will be a 1.5 bond like that. There will be 2 lone pairs that are on this. And then these extra lone pair will be spread out. And so we don't have a negative charge on this one, jumping to a negative charge on this one. It's going to be spread out over both. So it's a -1 charge divided by 2 oxygens. So it's a -1/2. -1 charge divided by 2 oxygens, -1/2. And these are what we call 1.5 bonds. They have more electron cloud density than a single bond, that is 2 electrons, but less than a double bond, which is 4 electrons. So 1.5 bond. When we do this, doesn't the hybrid structure kind of look like this? Wouldn't you say it looks similar to this? Yeah, it's pretty similar. And so there are people who say, you know, forget this stuff, just redo this, you know. Because we end up getting close to the same place anyway. But neither of these is totally the most accurate way to go. You know, valence bond isn't the most accurate way to go. What is the most accurate way to go? Valence bond theory is kind of the simplified quantum mechanical approach. You know, you simplify it to make things easier. You know, remember I was talking about classical physics? Was classical physics correct in its predictions? No, there was a problem. Remember, classical physics tried to describe the electron, but it was not successful. So classical physics, we found out that was incorrect. What's correct is quantum physics. Quantum physics is correct. However, it turns out that classical physics is a simplification of quantum physics. If you take quantum physics and you assume that you're working with large bodies, then the equations in quantum physics simplify into the equations of classical physics. So that way you don't have to approach every single thing quantum mechanically, and it makes your life easier. And so valence bond theory is a simplified approach of the full quantum. So valence bond theory would be like classical. You know, the analogy is not perfect, but it would be in that same vein. I remember doing this as a student. And I remember my answer I put down. we have this, and then versus this. This would be the octet, this is the expanded. How many resonance forms can I draw for this? This is bisulfate. How many resonance forms can I draw for bisulfate? Two? What are they?
Two more.
Oh, two more? Okay, altogether 3. That's correct. And then one more I'll draw this way. So the most accurate picture for this would be the hybrid. And what will the hybrid look like? It's getting harder to see. Let me draw it over here. So the pi bonding electrons are smeared out over these 3 bonds like that. And then we have 2 lone pairs that are fixed on each, and then a lone pair that's spread out over the 3 oxygens here. So what is the bond order here? You see them? The pole's right in the way.
Yeah,
Huh?
it's subconscious.
Okay, can you see it or not?
Yeah, I can.
Okay. What is the bond order here? Each one has one bond that's fixed.
1.3. SP3,
Close. Hmm?
SP3, SP3.
We're not going to worry about the hybridization of this. The bond order would be,
1.6.
is it a single, double, or somewhere in between? It's somewhere in between. Is it halfway? Is it a 1.5? It's not a 1.5. And so the easy way of doing it is we have 2 pi bonds. Do you see that? 2 pi bonds. And so it's 2 pi bonds spread out over 3 bonding positions. So it's a 1.67 bond order, or 1 2/3 bond order. What is the charge on each oxygen? Yeah, it's spread out over 3, so it's -1 charge spread out over 3 oxygens, so each one's -1/3. So when we do the double bonds and we reduce it to minimal formal charge, then it's easy to compare. Which one's more basic? This one or that one? Which one is a stronger base? Bisulfite or bisulfate? A stronger base. Bisulfite. This is the stronger base. This is the weaker base. And it boils down to this. Negative 1/2 is more negative than negative 1/3. That's it. If we didn't expand the octet and just looked at these, in organic chemistry, we would have said this also. We would have said the more resonance forms, the more stable. So over here, we only drew 2 resonance forms. Over here, we drew 3 resonance forms. 3 resonance forms are more stable. We get more delocalization. But let's compare these two without expanding the octet, because here we have no resonance forms. So if we look at these two, which one is a stronger base, and why? Well, we'll just look at one of the oxygens. So if we look at just one of the oxygens, you know, which one is going to have more negative charge density on the oxygen? This one or that one? This one, why?
Because the sulfur is going to give more electrons to the oxygen as opposed to that one. That one's going to be more electronegative.
Yeah, that sulfur is going to be more electronegative. So what you can say is this is a plus sulfur. It's going to have less of a pull. And that means oxygen is going to take more of the electron cloud density. Versus this one's a +2 sulfur, so sulfur will have a stronger pull. Oxygen is still stronger, but sulfur will have a stronger pull. And then for the negative charge density, it's less here. And so negative charge density, this is more of an inductive effect here. And so there are a lot of structures that you analyze using resonance forms and this type of stuff. And so this type of stuff is still quite useful for organic chemistry. Versus that type of stuff we'll totally miss if we just look at these on expanded octet structures. There's still other structures where we don't have to expand the octet and we can get a lot of resonance forms. Like the one we were looking at yesterday. Let's go back to the one we were looking at yesterday. I'll just back up a little bit here. Do you remember this structure, correct? Yeah, okay. We have names for the sites on the carbon here. Let me tell you what the names are. These 2 carbons are called orthocarbons. And then these two carbons here are called metacarbons, or carbons in the meta position. And then this carbon here is called a para. So if you flip back in your notes and you look, we had the negative charge on this ortho here, and then we could move it. We move the double bond here and kick these ones out. That puts a negative charge on the para. And then if we move the para electrons over here at double bond, it kicks these out and puts it in the other ortho position. Do you see those? And so does the negative charge ever end up on the meta position? So look at the resonance forms. Did you see the negative charge go on to the meta position? In other words, the lone pair ends up on the ortho and the para positions only. Not the meta. So the basicity of this is going to be sensitive to what we put on the ortho and the para positions. And so what we can have is we can have some substituents. So we'll substitute a hydrogen with something else. So we'll move the hydrogen and attach something else. So we could attach something like a methyl substituent. Or maybe I should draw like a radical there. So I'll remove the hydrogen with the electron and put this there. And so we have a methyl group there. Is a methyl group electron rich or electron poor, or just kind of in the middle? What would you say a methyl group is? It's rich, yeah. So that means it's an electron pusher or electron withdrawer? It's electron pusher. So let's say I erase this and put a methyl group here. Does that make this more basic or less basic? More basic. So electron pusher groups will make this more basic. Let's throw in a different group. Let's put in the nitro. This is called the nitro group. The nitro group is going to look like this. So I'll remove this and put the nitro there instead. Is that going to make it more basic or less basic? It's going to make it less basic. It's going to suck negative charge density out of this. So electron withdrawal groups will make this less basic. Electron pusher groups will make this more basic if those groups are on the ortho position or the para position. If they're on the meta, it's not going to make as big of a difference. But in the ortho and the meta. So that's a nitro group. This is called a chloro group. So if I put a chlorine there, is it going to make it less basic or more basic? What do you think? Bigger. If I put a chloro on here, it will make it less basic. It's electron withdrawal. It's electron withdrawal because of electronegativity. It's going to have the inductive effect here. A nitro group is very interesting because the nitro group here, what's the hybridization on nitrogen in the nitro group? It's sp2. So if nitrogen's sp2, then what that means is that we can have resonance delocalization into the nitro group. There's already resonance here. There's one more resonance formed here. And so we can push like a double bond out here, kick electrons out. And then we can get even more delocalization. And so nitro will have some inductive delocalization due to the positive nitrogen here, and resonance because we can have the double bonds extend out here. That'll make it less basic. Well, the weaker the base, the weaker its conjugate acid or the stronger the acid? The weaker the base, the stronger the acid. And so let's take a look at some of the acids here. And so the first thing is that, I think I already mentioned this, that this is not an ordinary alcohol. Ordinary alcohols are marginally acidic. In fact, they're so weak, we don't really consider them acids. So ethanol, you don't really consider that an acid. You know, ethanol is just an alcohol. And it wouldn't neutralize many bases. But phenol is, this is phenol. Phenol is, and that's primarily due to resonance delocalization of its conjugate base. There's going to be some slight, inductive effect because this is a positive formal charge. Or it's not, actually, that's not a positive formal charge. This is zero formal charge. And so these benzene rings, even though most hydrocarbons are electron pushers, most hydrocarbons are electron rich, they burn. Benzene burns too. Benzene is highly flammable, so if you have a benzene fire, it's very dangerous. However, this one is an electron withdrawer. How can this be electron withdrawer and still be a good pusher? That is electron rich. How can it be still electron rich? And the answer is because of the conjugated pi bonding network, which makes this an aromatic compound. And so we have this ring of delocalization here, which we typically show as this. This is the shorthand way of writing benzene, organic chemistry. And then we have this alcohol, like this. Having this conjugated pi bonding network makes this unusually stable. So the bond order is 1.5, but it's stronger than a 1.5 bond. I talked about this yesterday, correct? Stronger. And so phenol is unusually acidic. This is more like acetic acid than cyclohexanol. So what types of things would make this more acidic? What types of things would make it less acidic? And that depends on what we put as an R group here on the ortho position and an R group here on the para position. Those are going to have an impact on the acidity and basicity of this. And so if we put an electron withdrawer An electron withdrawer would be like nitro, chloro, something that can remove electron density. Then does that make this more acidic or less acidic? More acidic? Yeah, it makes it more acidic. Number one, it makes it more acidic because an electron withdrawal here will have an inductive effect. So it's going to try to take some of the electron cloud from the benzene ring here, which in turn will try to take electron cloud from here, which will make this more positive. And number two, an electron withdrawal in the ortho or the para will help stabilize the negative charge that ends up on the ortho and para positions. If we end up with negative charge in the ortho and para, if we have an electron withdrawal, that's going to help stabilize it. And so electron withdrawal makes this more acidic. This is for the R group. Whereas an electron pusher will make it what?
More basic? I mean, less acidic, sorry.
Less acidic. We'll call it less acidic. Less acidic means the conjugate base is actually going to be stronger. And so make it, you know, the conjugate base more basic. The one final thing here I want to talk about is this aromatic structure here. And we get this delocalization over the entire ring here because of how the p orbitals line up. And so if I'm going to draw this in a partial side view. Actually, if I look at the p orbitals, they're going to be like this. Drawing is not so great, but what we'll do is we'll connect all the upper lobes here and then all these lower lobes here. And so we can see how the pi bonding, the pi electron cloud is going to be spread out over the entire ring. So this is what we get when we have alternating single, double, single bonds. We'll have a total delocalization of the pi bonding or pi electrons over the entire conjugated pi bonding network. The sp2 sigma bonds, just shown here, they'd be just flat in the plane with our sp2s. This would be the sigma bond. The sigma bonds are going to be localized. However, the pp pi bonds are all going to be delocalized. This would be the pp pi bond. Shown in purple here. Probably should have gone with the same color. So if we have something like this, what's the hybridization on this carbon? Hybridization you predict would be sp3. Now, if we have sp3 carbons, that's going to put a kink in the ring. And so when we have sp3 carbons, it zigzags. We could see this with cyclohexanol. Let me do cyclohexanol one more time over here.